My name is Tyler Jaszkowiak, and this project is about the use of latent codes to encourage exploration in deep Q learning. In the branch of artificial intelligence called reinforcement learning, an agent must learn to interact with its environment without being explicitly told the correct way to act. Feedback may be given to the agent only very rarely. It must learn what environment states are good and what actions are valuable based on an infrequent reward signal. At each time step, the agent receives a state description from the world and picks an action to take. Based on this action, the environment gives the agent a reward and a next state. The agent is tasked with learning the relationship between state-action pairs and the reward it can expect to receive in the future. In deep Q learning, the state is represented only by pixels on the screen. The agent uses a convolutional neural network called a deep Q network to estimate the expected future reward of taking each action in a given state. In this project, I evaluate the performance of deep Q learning on an environment called Mountain Car. The agent controls a car which is initially placed at the bottom of a steep valley. A reward of -1 is given during each time step, unless the vehicle has reached the flag at the top of the right side of the valley, in which case a reward of 100 is received. However, the vehicle does not have enough power to drive up the right side of the valley directly, so it must learn to build speed by rocking back and forth. The state is represented by the pixel values from the last 4 time steps, so the agent can make inferences about velocity as well as position. There are 3 actions: accelerate to the right, coast, and accelerate to the left. Before it can learn a good policy, the agent must explore a sufficient amount of possible states. One way to do this is to select a random action with probability epsilon, and otherwise take the action the network believes leads to the highest future reward. Epsilon is initialized to 1 and decreases to 0 over time. In complex environments with large state spaces, even this method can result in the agent exploring only a very small region of the complete set of possible states. I seek a method to encourage more thorough exploration. In order to encourage the agent to explore more areas of the state space, I have it give itself a reward in addition to that received from the environment. In this work, this intrinsic reward is given for reaching states unlike those it has observed before. This is accomplished using what's called the latent code from the deep Q network. In its last layer, the network learns to express the state as a vector of numbers before using this vector representation to predict the future reward corresponding to taking each action from that state. In order to provide an additional reward for reaching novel states, these latent codes are stored in an archive. At each time step, the agent gives itself an additional reward proportional to the distance of the current state from the nearest state in the archive. Unfortunately, the added reward does not seem to significantly affect the frequency with which the agent reached the flag. This chart shows the average reward per 100 time steps over time. The original deep Q learning algorithm is shown in green, and my modification with intrinsic motivation is plotted in gray. The original algorithm reached the flag in fewer time steps, but also reached the goal 5 fewer times than my version. This seems to be only due to randomness. Note that both versions appear to be reaching the flag more frequently as time progresses, highlighting the success of the learning algorithm. This video shows a fully trained network solving the problem without taking any random actions. It only uses what it's learned in training to reach the flag. There are some things to be learned from the plot of external reward and intrinsic reward over time. In this chart, the external reward is shown in green with abrupt spikes when the flag is reached. The intrinsic reward is shown in gray. The first thing to note is the high magnitude of the intrinsic reward received in the first 2,000 time steps. At this point, nearly every state is novel to the agent. In addition, the deep Q network is getting its first information about the environment and adjusting its weights by large amounts. As a result, the latent code representations of the states tend to change significantly as well between time steps. Eventually, the intrinsic reward stabilizes. Secondly, notice the abrupt increases in intrinsic reward following the agent's first, second, and third successful traverses up the hill. The agent has just received a reward that was large and positive for the first time, which is very different from the rest of its experiences. The network weights must be updated to account for this information. As a result, the latent code representations also change. In the current implementation, the network only tries to approximate the future reward expected from taking each action. It learns features that are relevant to this task, but not necessarily useful for the task of deciding which states are unlike previously observed ones. If the network were simultaneously trained to also recreate the pixel representation of the state from its latent code, more meaningful latent code representations might emerge. An intrinsic reward signal based on these may help to increase the learning rate.